So today we're going to study a thing called the real zeros of polynomial functions. There are imaginary numbers, but I don't have time to do that this year. Now, a polynomial function f of degree n greater than 0 has at most n real zeros. Now, here's what you need to remember, that some of them are not necessarily distinct. I.e., you could have, for example, something like this. F of x, when you factor it, equals x plus 1 times x plus 2 squared, right? Now, the original function is x cubed plus blah, 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 plus 2 is our answer. What it would be. But you notice its power, the power of the original function f, the greatest power, the degree, is 3. But you'll notice that the terms in front, the factored form of this is there's 3 individual factors, but one of them is being repeated twice. So, i.e., you have x plus 2 being repeated twice. Now, here is some caveats for the function f that we were talking about before. Here's some things that you need to know. F may not have any real roots. I.e., you go to solve and then you have one value is like the square root of -1, right? So f may have also m roots, where our m value is less than our n value, i.e., there are a few roots that you can't figure out because they're not real, and the other ones are easy to come up with, okay? Here's another thing. F has at most n real roots. And the last part here, f has at least one real root if n is odd, i.e., the exponent. Okay, all right. So let's go through this problem set. I might introduce you to a complex root later on, and when you see it, you'll make sense of it. All right. So I need you to recall the following about mathematics, about numbers. Recall that r, the real numbers, is equal to stuff that can be written as a fraction and stuff that can't be written as a fraction. Okay, so these are numbers that can be written as a fraction, and this is what we're actually going to be focusing on today. So recall this. For any functions, for any numbers in the real numbers that can be written as a fraction, the q value, we call it q. Notice how I'm writing q, nice script. So is basically the set where p over q, where you have p over q, where p and q are integers. And the q value is not equal to 0. All right. Now, here is the rational zeros theorem. I just want you to copy this down and then I'll talk about it. Okay, so here's the deal. With this theorem, I want you to just copy this down. When you have a fraction p over s, right? If I say that p over s is a root of the function f of x, that means the whole thing's equal to 0, i.e., if I find a fraction of p and s, where p is the integer factor of the last term, and s is the integer factor of the first term, then if we have some sort of related combination of one of the factors of p over s, that means we could easily find a root. So let me give you an example of what we're actually saying here. So suppose I have a function with possible rational zeros. So imagine the function looks like this. F of x is equal to, let's say, something x to the n, something, let's say it's x to the 5 plus blah, 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 a whole bunch of ugliness. And then we have our last term. And our last term is a constant, okay? Our last term is, and the first term of our problem is, say, 2. Okay? So the leading coefficient of our problem is 2, and our end term is 10. Now, here is what I want you to do. When you see a problem like this that's fully expanded, what you have to do is I want you to label this one P and this one S. The front is S, i.e. the start, and the 10 is the posterior, the end, right? Another name for n. So S is the starting coefficient and P is the final coefficient. Now, here's what we have to do. I want you to list the factors of P of 10 of P and S. So the factors of 10 are the following. You have the following for 10. Plus or minus 1, plus or minus 2, and plus or minus 5. You can also have for S, plus or minus 1, and plus or minus 2. Now, based on this, right, that theorem that we were talking about before, what you're going to do is literally just find all the possibilities of P over S. So here are the possible zeros. And all we're going to do is we're going to take some factor over the top here, divided by something over here. By the way, we need to also add plus or minus 10 for this next problem. So here are my plus or minus, here are my possibilities. So my possible zeros would be, well, plus or minus 1, because I got 1 divided by 1. I could also have plus or minus 2, plus or minus 5, and plus or minus 10. Now, we could also have fractions as well. We could have plus or minus a half and plus or minus 5 halves. So now, here's where this comes from. I didn't give you the original equation, did I? So imagine I started with a function like this. The actual function that I'm going to give you would be, say, f of x is equal to, well, 2x cubed minus 7x squared minus 17x plus 10. A long time ago, you wouldn't be able to factor that, right? But now, here's what we did. We went and identified the S, the starting value, and the posterior value, and then we made ratios of P over s, and we just explored all the p over s's, right? Now, when we explore all the p over s's, if I wanted to find if this was a possible zero, all we have to do is just test. Test if one of these values that we had here, one of the values that we had here works. So let's test if the following works. Well, f at, say, 1/2. So when we punch that in, you can just set it up by subbing in and then punching it all into your calculator. So you got 2 times 1/2 cubed minus 7 and 1/2 squared plus 17 times 1/2 plus 10. Punch that all into your calculator and boom, this is a 0. So f at 1/2 is 0. So that means x equals 1/2 is 0. Or you could say the following. Or you literally could say the following. So we have x minus 1/2 is a factor. So from here, we could go and do division of our polynomials and find the quotient, the divisor, and the remainder based on the fact that I have this thing. X is 1/2. X minus is our factor. So let's go and do some sample problems. And we will continue this problem with an extension, okay? So once we found that f of 1/2 is 0, we can use synthetic division to continue solving our problem. So imagine I've got my little problem here, and I need to basically divide out. So we want to use synthetic division. Synthetic division on f of x is equal to 2x cubed minus 7x squared minus 17x plus 10. And we found that f of 1/2 was equal to 0, right? So that means that the c value that makes this thing equal to 0 is 1/2. So now that I've got that, what I can do is I can actually apply synthetic division. And synthetic division is just so compact. We can literally do this in one spot, in one shot. So if I do synthetic division, you're going to have something like this. You're going to have, from your f value, you're going to have 2, -7, -17, and 10 as our individual numbers. Now, our c value is 1/2. So we put 1/2 in front. Then what we start doing is we bring down the 2. Then we take 1/2 times 2, which is, well, it's just 1. -1 plus -7 is 1 plus -7 is -6. Then we take -6 multiplied by 2 by 1/2. You get -3. And then you end up with -17 plus -3 is -20. And then -20 times 1/2 is -10. And we end up with a remainder of 0, which is what we should get because we know that this thing here, f of 1/2 is 0. So that means x minus 1/2 is a factor for this problem, right? So here's what you write. So now we got 2, -6, -20, and 0. So then you can say, then the factored form of fx is this. Fx is equal to, well, remember our original equation. Don't have to write it. We can just write x minus 1/2 from here times the following, 2x squared minus 6x minus 20. And then from there, we can take this and easily factor it. We can pull out a 2 to begin, and we end up with 2x minus a half times the following. X minus 3, so x squared minus 3x minus 10. So we pull out that 2, so now we can factor off the last bit, so we get 2x minus a half times, well, x minus 5x plus 2 is our final answer. And so now that we've got all of that, I could say, therefore, the actual rational zeros are given by this. And so you could say the actual rational zeros for f at x are the following. Well, 1/2, 5, and -2, based on these things that we have here, here, and here. And we're so let's say we have the next problem here. Let's call this problem 2. So we have fx is equal to 3x to the 4 plus 5x squared plus 1, right? So remember, we have to identify the start and the posterior of our problems. So the posterior of our problem starts with p. So p's values could possibly be plus or minus 1. But s's values could be plus or minus 1 and plus or minus 3. Which means that if I'm taking a look at p over s, we have these possible values. Plus or minus 1 or plus or minus 1/3. Now, those are all of the possible zeros. You literally have to go and look for it, right? If I look at this original problem here for f of x is equal to 3x to the 4 plus 5x squared plus 1, you got to understand that clearly the positives won't work because these are all positive values that we have here. These are all positive values, and if you're adding positive values, no matter what happens, you're always going to get positive. So we got to start using negative values and hope to God that something works, right? So clearly in this case, there are no positive zeros. So so none of the plus 1/3 or whatever works. And we should check to see if the negatives work. So if I punch in f of -1, I notice that I don't get 0. If I punch f of -1/3, guess what? I don't get 0. Because none of them work, you can say, therefore, there are no rational zeros for our function f at x. All right, so just take that in and understand what's going on, and we'll move on to the next. So imagine I have the following equation. F of x is equal to this equation, right? Now, remember, we're always going to identify our p, our start, and our p value, okay? So our p values, possible factorizations are plus or minus 1 and plus or minus 3. And our s values are, well, plus or minus 1, which means our P over S calculations are the following. The possible factorizations are basically plus or minus 3 and plus or minus 1. So these are all possible zeros. So the key idea here is you try your best to find something that works, right? I know that when I calculate f of -1, I'm going to get -1 to the 4 plus 2 times -1 cubed minus 2 times -1 squared minus 6 times -1 minus 3. Calculated. Oh my goodness, it's 0. So here's what we can do. Our C value is -1 and x plus 1 is a factor. You can put that down as something that we can use later. So now we have C is equal to 1, so now we can do synthetic division. We start with our function, set up all our values. 1, 2, -2, -6, and -3. Then we go and set up our addition table, and we use our C value of -1 because -1 is a 0. So then we just bring down our 1, and then we fill out the rest. So we have this for our final calculation using our synthetic division. And so that means our function is this. So every time you go and do your synthetic division, tell me what your function looks like as a factored form. So we have x plus 1 times x cubed plus x squared minus 3x minus 3. So now here's what we do. We need to go and factor this. So here's what I do. I let g of x equal x cubed plus 2x squared. So that factored, that thing that I want to factored, minus 3x minus 3. And we do exactly what we just did for the rest of this problem. So now we're going to do for g of x what we did for f of x. So you're going to find that g of -1 is equal to -1 cubed plus -1 squared minus 3 times -1 minus 3. Then we're going to do synthetic division. Division again. And we end up with, well, that's equal to 0. So that means that we have another C value equals -1, which means we have another x plus 1 being a factor. So now we can go and write our solution by doing our synthetic division. And we end up with our g values put in 1, 1, -3, -3. We punch in -1, bring down the 1. So notice every time you do these, you're always going to get a remainder of 0 because our functions always factor. So now when we go and write our solution, this is what we have. So we have 2x minus x plus 1 squared. So f of x. So f of x is equal to x plus 1 squared. But then we can get the rest of our problem from this part here. Now remember, it's 1 power less than before, so we're going to have x squared plus 0x and then minus 3. Now we can factor this last part to be x plus 1 squared times x minus the root of 3 times x plus the root of 3. So now you can say what the rational zeros are for this following problem. So now we can say, so the rational zeros are, you'll notice we have everything set up in such a way that we have almost a linear set of terms. So the rational zeros are given by this. X is equal to -1, and then plus or minus the root of 3. And there we go. We're done. But these ones here are irrational. So if we had said that the roots are this, then plus or minus 3 couldn't work here. So technically, we can only say that the rational roots are just -1, and their multiplicity is 2. Now, if I asked you for all of the roots, you would have said -1 and plus or minus root 3. So just remember that these ones here are called irrational roots. And the only time I want them is if I ask you just specifically for the roots. But if I ask you for the irrational roots, you must do them.